In this video, we're going to answer a simple question. How does a 1.4 million kilogram rocket actually leave the ground? The answer is hidden in a single equation, Newton's second law. Force, mass, and acceleration. And it all comes down to this. F equals m times a. At first glance, it looks simple. But by the end of this video, you'll see just how deep this equation can go. Now, let's bring this into the real world. What you're seeing on screen is the Falcon Heavy rocket, one of the most powerful rockets ever built. It has 27 engines, and together they produce about 22 million newtons of thrust. The total mass of the rocket? About 1.4 million kilograms. So let's do what every physics student would do. Let's plug in the numbers. 22,819,000 equals 1,420,788 times a. Solving for acceleration, what we get is approximately 16 meters per second squared. Sounds impressive, but is it actually correct? Pause for a second and think about it. Because this number is completely wrong. Why? Because we forgot something important. Gravity. In our calculation, we treated the rocket as if the engines were the only force acting on it. But in reality, Earth is pulling it down the entire time. So instead of looking at just the thrust, we need to look at the net force. The real equation becomes thrust minus gravity equals mass times acceleration. Now, let's fix our mistake. When we subtract the force of gravity, the net force drops significantly. And when we calculate the acceleration again, we get about 6.28 meters per second squared. That's a huge difference, from 16 down to 6. Now this is much closer to reality. But here's the real question. Is this finally correct? Well, for a basic physics problem, yes. But if we want to think like engineers, we're not even close. Because there are still forces we haven't included. For example, air resistance. As the rocket climbs, it has to push through the atmosphere, and that creates a force in the opposite direction. To calculate that, we'd need detailed aerodynamic data. We don't have the exact data, but we can still represent it in our equation as F drag. Addition to that, there's more that affects net force. Rocket engines don't instantly reach peak efficiency. Right at ignition, performance is lower. So even our thrust value isn't perfectly accurate at the start. So how good is our estimate? Let's compare it with real data. The first few seconds of a launch are messy, so we'll skip ahead to the 10-second mark. At 10 seconds, the rocket is moving at 123 kilometers per hour. At 11 seconds, it's at 142. That's a change of 19 kilometers per hour in just 1 second. Converting that into meters per second squared, we get an acceleration of about 5.27, which is very close to what we calculated, but still slightly lower. So, are we done? Not even close. Up to this point, we've been using a simplified version of reality. Now, things start to get real. Because in reality, nothing here is constant. As the rocket gains altitude, gravity gets weaker. Air density drops, which means less drag. So the forces acting on the rocket are constantly changing. Every second, every meter. And it's not just the forces. The mass changes too, because the rocket is burning fuel and getting lighter, which means the equation itself is changing over time. So instead of a simple equation, we now have a system a system where force changes, mass changes, and acceleration responds to both. And when you put all of that together, that simple formula we started with suddenly becomes something much more complex. And that's the beauty of physics. A single line, F equals m times a, can describe something as powerful as a rocket leaving Earth. But only if you're willing to look deeper. If you enjoyed this video and want to see more content like this, consider subscribing to my channel. And if this helped you understand physics a little better, leaving a like really helps. Thanks for watching.